Chemical bonding resonance structures. In this tutorial, we will be going over resonance structures, an ozone example, and a formate example. When drawing a Lewis structure for a chemical species composed of multiple covalent bonds, more than one possible Lewis structure may be drawn for that species. The possible Lewis structures are called resonance structures. Resonance structures have the same order of bonded atoms, that's really important, but with different electron arrangements. The actual structure is the average of the possible Lewis resonance structures and is called a resonance hybrid. All bonds in the resonance hybrid are considered equivalent in length. That is, the actual bond length is an intermediate between a single bond and either a double or triple bond. In the Lewis model, electrons are localized either on an atom as a non-bonding electron pair or between atoms as a bonding electron pair. However, electrons are often delocalized or spread out over several atoms or bonds, resulting in an overall lowering of the potential energy for the resonance hybrid. The lowering of potential energy due to the delocalization of electrons is called resonance stabilization. Let's look at the example of ozone. In ozone, we have 3 oxygens, each with 6 valence electrons to give us a total of 18 electrons. So the total number of electrons is 18. That means we have 9 electron pairs to work with. So we have 3 oxygens. So I'm just going to draw 3 oxygens in a row. So 1, 2, 3. Now, I have 2 electron pairs that have been used up and 9 electron pairs to work with. So 7 electron pairs to distribute between these 3 oxygens. So I'm going to do what I've normally done, thinking that this oxygen is my central atom, and I'm going to use a straight line to represent a non-bonding electron pair. So if this oxygen needed all of its non-bonding electron pairs, it would need 1, 2, 3, and then I'd have 4, 5, 6 to fill up that oxygen, and then 7, 8 if everything was going to get a full octet. So how many lines am I using here? So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, well, I only have 9 electron pairs to work with, which means either one of the non-bonding pairs on this oxygen or one of the non-bonding pairs on this oxygen needs to be removed and made into a double bond between 2 of the oxygens. So let me erase this and redo it. Now that I know that I need a double bond between 2 of the oxygens, I'm going to make a double bond right here. Now that I have that double bond, let me go put my other non-bonding electron pairs in. So 1, 2, 3, 4, 5, 6, 7, 8. I have 1 more electron pair to work with. I'm going to put that on my central oxygen. And now I have 9 electron pairs, either as shared electron pairs or non-bonding electron pairs. Now you might say, well, what is the resonance structure for this? The resonance structure of this would be, and I'm going to put a double arrow saying that there can be another resonance structure, is basically the mirror image of this particular structure. So instead of a double bond being located in this location, the double bond is now going to be in this location. So I'm going to put 3 oxygens in a row again. 1, 2, 3. Put single bonds to represent shared pairs. Put a double bond right there. And then put my non-bonding electron pairs in. So I have 1, 2, 3, 4, Now that oxygen is in good shape. 5, 6, 7, 8. And that last non-bonding pair will go on my central oxygen, 9. So these are the two resonance structures of ozone. Now, when we get into molecular geometry in the next unit, we're going to see that ozone is not a linear structure. Instead, this lone pair on the central atom here and here will actually influence the bond angle for the double and single bond here and the single and double bond over here. So what ozone will really look like is seen down here, where this lone pair throws up these huge electron clouds and ends up pushing these bond angles down. But like I said, we'll get more into that in the next unit. The ozone molecule has two equivalent O-O bonds whose lengths are intermediates in length and strength between a single bond and a double bond. Ozone is often described as having 1.5 bonds. Now, how is this 1.5 bond represented? If we go to this last image right here, this dotted line right here is basically showing the 1.5 bond, that these bond lengths right here are somewhere in between a single and a double bond. So this diagram right here is demonstrating that ozone is composed of resonance structures. Let's look at another example. Draw two equivalent resonance structures for the formate ion HCO2-1. Let's see how many electrons we have to work with. We have one hydrogen involved with one valence electron to give us 1. One carbon, 4 valence electrons to give us 4. 2 oxygens, 6 electrons apiece, that gives us 12. We have a -1 charge, so our charge is going to be added in with 1, and that will give us a total number of electrons of 18, which is the equivalent of 9 electron pairs. So I want to draw this resonance structure just in the order that I see it. So it's HCO2-1. So I'm going to draw a hydrogen attached to a carbon, attached to an oxygen, and then attached to another oxygen that I'm going to put straight upwards. And again, I'm going to use a red dash initially to figure out how many lone pairs I need. So I have 3 shared pairs going on. That means I have 6 electron pairs left over. How many more electron pairs do I need to give everything here a full octet? Well, this oxygen needs 3 non-bonding pairs. So 1, 2, 3. This oxygen needs 3. 1, 2, 3. And this carbon needs 1 more. So if I count up my blue and red lines, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need 10 electron pairs. I only have 9. So that means I'm going to make a double bond either here between this carbon and oxygen or here between this carbon and oxygen. So I'm going to erase my red lines and add a double bond between one of my carbon-oxygen pairs. So I'm going to add that double bond between my top oxygen and my carbon, and then I'm going to fill in the remaining non-bonding electron pairs. So 1, 2, 3, 4, and then I have 5, 6, 7, 8, 9. And everything here has its full octet. The hydrogen has its duet. The central carbon has 4 shared pairs to give it its 8. This oxygen has 2 non-bonding pairs, 2 shared pairs, and this oxygen has 3 non-bonding pairs and 1 shared pair. So what is the resonance structure for this? Well, the resonance structure just means that instead of the double bond being located here, the double bond is now going to be located between this carbon and this oxygen. So if I redraw this, I have my carbon. I'm going to put a double bond here. I'm going to put a single bond with an oxygen up here. Lone pair, lone pair, lone pair, and then just two non-bonding pairs right here. And now I have my two resonance structures. So the electrons have shifted from one oxygen over to the other oxygen. Now, what would this look like if we saw this with the correct molecular geometry? It would look something like this down here, where these non-bonding electron pairs actually end up pushing down these bond angles, which again we will talk about more when we talk about molecular geometry. But the true resonance structure is somewhere in between these two structures. So the resonance structure, this dotted line right here, represents these intermediate bond lengths between a single and a double bond, which is why these bonds are more accurately defined as being 1.5 instead of single or double. So what did you learn in this tutorial? We defined the concept of resonance structures, we looked at an example using Ozone, and then we looked at an example using Formate. Need more help? Feel free to contact me. Have a great day.